Calculating it is pretty straightforward if you have technology especially. But making sure you know what it means is infinitely more important in my humble opinion. So when you look at a poll and you look at its margin of error, you know what it's implying. Go ahead, Allie.
So if there's a smaller sample size, is it a higher margin of error?
The larger number?
Yeah.
Think about what Allie I want you guys to answer Allie's question. Allie's looking at these margins, 2%, 4%, 5%, 15%. Which ones do you think have larger sample sizes? The smaller margins or the larger margin? Let me see hands on this one. This is a cool, intuitive, matched with mathematics question. I want you to go purely on intuition right now. Chris?
The higher your sample rate, the lower your margin.
We in agreement with that? Second? All in favor? Any opposed? Discussion? Well, I think we should have discussion about it. Why?
Because it's closer to your population.
Love that answer. Because if you've sampled more of your population, you should be less uncertain in your result. The uncertainty is the margin of error, right? It's the uncertainty is that margin. The margin should decrease as your sample gets larger. Yes. Could you ever shrink your margin to 0? Well, unless you do the whole population. Because then you wouldn't need a margin, right? If you had the whole population, you wouldn't need a margin, but there'd be no error. There'd be a lot of caffeine and a lot of lost sleep, but there would be no error. There'd be no margin. Good, good. Yeah.
Wouldn't there be some error though on people that like to fudge stuff? So
That's
still
called
margin?
non-sampling error. Thank you, thank you. This word error right here is sampling error, which means you did everything right, but there's still a bit of randomness in the population. Remember how we said we got 112 here? If we did it again, we wouldn't get 112 again. We'd probably get 114 or 108 or who knows, 120. That's called sampling error. It's natural variability in the population, just like everybody in this room is a slightly different height. Even if you're very, very, very similar in other characteristics. Normal variation. That's sampling error. Non-sampling error is what you're talking about. People fudging results, doing a biased sample or a biased questioning. That escapes the realm of statistics. We cannot control for that. That's why you're in this class. You're trying to learn it, and your research methods classes. You're trying to learn not to do that. Well, you can. You totally. Oh my God. You totally can fudge results. In your first project, you'll see how Lou Dobbs did it. I used to watch Lou Dobbs when he was on television. A question he asked one day, I'm like, seriously? Seriously, you're going to waste electricity, oxygen, and a graph on that question you just asked. And he did. But you're going to see how, even if the data he got was totally valid, it doesn't matter because it's crap because of what he asked. So, yeah, that two different, and your project deals with that quite depth,
That's
quite
the crazy
detailed.
making stuff.
It can make you crazy, for sure, for sure. Now let's just make sure we understand how to use these margins, yes? Suppose you had a margin of error of 2% on a 41.5% probability value. How would you apply that margin of error? Don't overthink this, it's very straightforward. Don't overthink it. What do you do with the 2%, Allie?
You subtract 2% from 41.5 and add 2% plus 41.
And that's the range of value. So what you say, the incorrect way of reporting the 41.5% is, there is a 41.5% chance that you're going to get heads when you spin a coin. Wrong! Wrong. That was in your sample. What you do is you do exactly what Allie said. And you do the p hat plus or minus that margin of error. You add and subtract it. So 41.5% minus 2% becomes what? Oops. 39.5%, right? Up to 43.5%. If I did my math right? So now what you say is not that there's a 41.5% chance. Not that there's a 41.5% chance. You say there is...
39.5 to 43.5%.
Good, I like that. I like to put the word between into. There is between a 39.5% chance and a 43.5% chance that you're going to get heads when you spin a coin and let it fall. Could we be wrong? Of course we could. That's because this is not a 100% confident statement. This is not a 100%. There is a set level of confidence tied to that interval. These are called confidence intervals that you're making right. I've used that term in 243. I don't know if Donna ever did or not. I introduced you to that topic back in 243 and then said, that's enough for right now. We'll get back to it in 244. But there's a set level of confidence attached to each of these percentages based on the sample size. But we'll deal with that fine point momentarily when we get into the actual computation of what we're doing. How about 5%? What would that look like? P hat plus or minus the margin of error. Make sure we can do this.
36.9?
Right, 36.5, yeah, mm-hmm. Up to 46.5. Would the confidence on that interval be higher than the confidence on the last one? Assuming the same sample size, which it is. Will we have higher confidence? For sure, yes. Tell me why?
Because it's a bigger number.
It's a wider interval, isn't it? It's a wider interval, which means you've got more of a chance of capturing that true value. The trick, my friends, is the true value is out there floating around between 0 and 100%. Your job is to throw a net up, which these guys are. The net gets thrown up and tries to catch it. The wider the net, the more confident you are that you have caught it. Make sense? Fair, hopefully fair. All right, good. 4%. I think you guys are getting the hang of this. That's going to go down to 37.5%, yeah. Up to 45.5. So all we're doing is taking that margin of error, adding and subtracting it from our point estimate and calling it good. Calling it good. And last but not least, 15% is going to go down to, is that 26%? Make sure I'm doing that right. And then up to 56%. Did I do that right, friends?
Yep.
Should be different by 30. Yeah, good, we're good. Now, if you check real quick, if you check your math, there's not much math to do, honestly, right? And subtracting. You check your math real quick, if you look at how far apart these are, they should be double that. So they're 30 apart, that's double 15, that makes sense. That's 8 apart, that's double 4, and so forth and so on. You see why it's doubled? Minus, plus, twice as wide. Good, 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 good. So what you've just seen is the basic construction of what is called a confidence interval. So let me give you one slide for starters. You'll have all these slides as soon as, I think I gave it to you last week on the schedule page. We'll have it reposted again today. One quick slide on the overriding principle